Hi guys, and welcome back to my channel. In this video we'll be discussing wave functions, and we'll also do a little bit of an introduction to the Schrödinger equation. So what exactly is a wave function and why do we need it, right? A wave function describes the wave-like nature of things we normally think of as particles. So for example, electrons, right? We normally think of electrons as a point particle. A wave function describes its wave-like nature. And the Schrödinger equation, what exactly is the Schrödinger equation? The Schrödinger equation is sort of the master equation in quantum mechanics that allows us to calculate the wave function for any particle. So they sort of go hand in hand. So why exactly do we need a wave function? And I touched on this on the previous slide, but we have this idea of wave-particle duality, where we have that particles have wave-like properties. We talked about this in the context of light, where light can be thought of as both an electromagnetic wave, a wave, or as a stream of photons, a stream of particles, right? So similarly with things we normally think of as particles, like electrons, these particles still have wave-like properties, and the wave function describes these properties. So we replace the trajectory of the particle by a wave function, which is denoted by the Greek letter psi. And we can see on the graph to the right, this red curve is psi, which is our wave function, right? So what is the Born interpretation? Now this is really important. The Born interpretation basically means that the probability density of finding the particle is equal to psi squared. So if we take our wave function and square the values, we get the probability density. And what does that mean, right? That means the probability of finding the particle in a certain region is equal to the integral under the curve of psi squared. So let me demonstrate this on the graph. So if we look at the blue curve, this blue curve is psi squared, and say I have these two x values, x equals 10 and x equals 11, just for example, right? Then if I wanted to know what is the probability, what is the chance that if I observe this particle, it's going to be between x equals 10 and x equals 11. All I have to do is take my psi squared and find the integral, find the area under the curve between these two spots. So if I found this area, right, that should give me the probability of finding the particle between x equals 10 and x equals 11. What does this also mean, right? Because psi squared is a probability density function. That means if I took my entire integral over all possible x's, so if I took this entire area, right? That means that that's basically giving me the probability that I find my particle anywhere across every x possible. So that should be 1, because I have to find my particle somewhere. So the total integral of psi squared, if I integrate over all x values, this should be equal to 1, right? Because it is a probability density function. So these are kind of important things to keep in mind. Next, we'll talk about nodes. So nodes is another important sort of vocab term, and that's very useful. A node is the location where psi passes through 0. So if we look at this on the graph here, psi, the red curve, passes through 0 at this x value, right? So this is a node. We have psi passing through 0. Also note that if we have psi equal to 0, this means that psi squared has to equal 0. And if psi squared is our probability density, what does that mean? That means that there should be no chance of the particle being found at the node. So that's another really important point, is that the particle will never be found at the node because psi squared equals 0. So this is kind of interesting, right? Say we look at this wave function here. The particle can be found, say at x equals 7. The particle can be found here at x equals 8. But right in the middle, x equals 7.5, you'll never find the particle. So this is kind of a weird thing to think about, that you can find it on the right or on the left, but in the middle, you will never find the particle. So this sort of goes to show how unintuitive a little bit quantum mechanics can be at times, but it's something to keep in mind. So what exactly is the Schrödinger equation, right? The Schrödinger equation is kind of like the F equals ma of quantum mechanics. So with F equals ma, with Newton's second law, right, we know that if I'm given the initial position of a particle, its initial velocity, and I know the forces that are exerted on this particle, I should know at all points in time where this particle is going to be. The Schrödinger equation, the time-dependent Schrödinger equation, is pretty similar, except it deals with wave functions now. So basically the Schrödinger equation says, if I know the wave function of a particle at one point in time, then I should know the wave function of the particle at another point in time. And the Schrödinger equation tells me how to find the wave function of the particle at a different point in time. So how to calculate the wave function for any particle is basically what the Schrödinger equation tells us. However, this gets very, very complicated in many cases, so we're only going to deal with certain simple examples, and the one key example we'll deal with is a particle in a one-dimensional box. So that's the key, easy example that we'll deal with. What exactly is the Schrödinger equation? The Schrödinger equation looks like the Hamiltonian operator operating on the wave function psi equals the energy of the wave function times the wave function psi. So what is a Hamiltonian operator? Hamiltonian operator is just this right here. We have negative h squared over 8m pi squared d squared over dx squared plus v of x. And v of x is our potential function. And this Hamiltonian applied to the wave function equals the energy, again, times your psi. And when we expand this Hamiltonian operator out, we get this equation right here. Sorry, there's a psi missing, but here's this equation is what we get when we expand the Hamiltonian times the wave function. So what we can, just some vocab, is that the Hamiltonian operator operating on the wave function, this wave function is called an eigenfunction of the Hamiltonian operator. So the wave function is an eigenfunction. And what is this? Why is it called an eigenfunction? Right? This means that when the operator is applied to the wave function, right? When we take our Hamiltonian and apply it to our wave function, we get a scalar multiple of the original wave function. And that's exactly what we get because our energy is a scalar. So when we operate our Hamiltonian on our wave function, we get a scalar multiple of our wave function because energy is a scalar. And our energy value is called the eigenvalue of our of this operation. So this is sort of kind of important terms to just know, because it comes up a lot in a linear algebra course or something like that, where you have an operator operating on something, right? And if that outputs a scalar multiple of that something you started with, that's called an eigenvalue or an eigenvector. In this case, you're calling it an eigenfunction. And the thing that it's being scaled up by is called your eigenvalue. Okay, so now we're going to look at the special example, which is the particle of mass m in a one-dimensional box of length L. And we're going to derive this in the next video, but just to give you what the actual wave functions are, you get, once we derive it, we get psi of n of x, psi sub n of x, equals 2 over L to the power of 1/2 times sine n pi x over L. And we get our energies, E sub n equals n squared h squared over 8ml squared. The energy is really important to sort of keep in your head as it comes up a lot, and it's very useful in calculations. What exactly is this n we're seeing, right? This n is called a quantum number. So what is a quantum number? And we'll talk more about quantum numbers in future videos. But a quantum number sort of labels or identifies a wave function. It's basically specifying some state. And we can use quantum numbers to calculate a value of some property of the system. So in this case, we're using our n quantum number to calculate the energies. So our n quantum number gives us the energies. Okay. And a really important thing to note is that we only have n's from 1 upwards, 1, 2, 3, and integers above 1. What this means is that n is not equal to 0. And if we see, that means that the energy can never be equal to 0, because the energy is equal to n squared h squared over 8ml squared. The lowest energy we can get is when n equals 1. So the lowest energy we get is h squared over 8ml squared. But basically, the lowest energy we can ever get is not equal to 0. And this is a really important point. This is called the 0-point energy. And we're going to cover this more in depth in a future video. But basically what this means is that our lowest energy is called our 0-point energy, but it's not equal to 0. And this is sort of consistent with our idea of the uncertainty principle, right? The lowest possible energy a particle can have cannot be 0, right? It cannot be 0, because if it's 0, that means it's perfectly still. And the uncertainty principle basically tells us that we can't be sure that a particle has 0 velocity, right, or has no momentum. That's basically what the uncertainty principle tells us. We can't be sure that there's 0 velocity. We can't be sure exactly of the position. So in this case, right, this lines up with the uncertainty principle. If we have 0 energy, if we have 0 joules as our lowest bar of energy, that means we would be sure that the particle is perfectly still in its lowest energy state, which wouldn't agree with the uncertainty principle. Okay, and we'll also talk about, later on, we'll talk about the kinetic isotope effect, and this is a really important application of 0-point energies. So now I want to look at the particle in a box, this graph, right, this diagram that we have to the right. So we can see that our lowest energy, that's here, our n equals 1 state, we have 0 nodes, right? We only have the 2 endpoints being 0. So we have 0 nodes in the middle. When we see n equals 2, we see that there's 1 node now. There's one time where our psi is crossing 0. When we go to n equals 3, we have 2 times where the psi is crossing 0. We have 2 nodes. And then you can keep seeing n equals 4, we have 3 nodes. N equals 5, we have 4 nodes. And n equals 6, we have 5 nodes, right? So you can see that there's an increase in 1 node per energy level. So this is sort of an important concept. Nodes increase by 1 with each increase in the wave function energy. And this is sort of a common idea when we're dealing with molecular orbitals, especially. When we cover molecular orbitals later on, we'll see that the nodes increase by 1 when we go to higher energy levels. And a molecular orbital is just a wave function that's describing electrons in a molecule. So instead of just a particle in a box, a molecular orbital is describing wave functions in a complicated molecule. And so the 2 main cases we'll see this happening is when we look at the wave functions of conjugated pi systems and aromatic molecules. And we'll see this common idea that our nodes increase by 1 every time our energy increases, and this can sort of help us figure out what the molecular orbitals look like. Finally, if you remember in a previous video, we derived the Rydberg constant using quantization of angular momentum, centripetal force, and Coulomb's law. Schrödinger actually used his equation and solved his equation when we take our potential function equals negative e squared over 4 pi epsilon naught r. And what is this potential function? This potential function is the potential function of an electron in the hydrogen atom. So when he solved his equation using this potential function, he ended up getting the same Rydberg constant that we derived in a previous video, which should sort of corroborate or show you that what we did was correct. Okay, cool. So that was all I wanted to cover in this video. I hope you enjoyed it and learned something, and I hope you'll stick around for some of my other content. Thank you again, and I'll see you in the next one.